In this lesson, we're going to look at how the strength of gravitational forces and electric forces change with distance and size. And these two laws are both inverse square laws, and they look a lot like each other. This is the force for a charge, and it says force equals K times Q1, Q2 over R squared, where Q1 and Q2 are the sizes of the charges. And the other one for gravity says F equals G M1 m2 over r squared, where m1 and m2 are the masses of the two objects being attracted gravitationally. K and Q are constants. K is 9 times 10 to the 9th Newton Coulomb squared per meter squared. Per Coulomb squared. Whereas G is 6.67 times 10 to the negative 11th Newton meters squared per kilogram squared. Now, those two things I'm not going to get super worried about, but it is worth noting that this is 9 followed by 9 zeros, and this is 0.007 more times 667. I guess 8 more times. So this is a really small number, and this is a really big number, and that's because the force due to charge is really, really big. The force due to gravity is really, really small. We just notice this one because Earth has a lot of mass. We don't notice this one because most things don't have charge, but when they do even have a slight charge, we notice that. We notice the static clinger when we get a little static buildup, our hair stands up, right? So a little bit of charge can cause big forces. Now, what I'm more interested in is what happens when we change things. So I say it's an inverse square law, and really I'm going to write it like this. Force is directly proportional to mass and inversely proportional to distance, right? In both of these cases, r is the distance between things. So I have m1 and I have m2, and then the distance between them is r. Now, if this force, if object 1 and object 2 and r squared, if they, whatever they are, if they have a force of attraction between them of, say, 20 newtons, and I take and I make m1 twice as big, well, what happens to that force? Well, if I multiply one side by 2, I have to multiply the other side by 2. So doubling one of the masses doubles the force, right? So this results in a force that's also times 2. But what happens if I double that distance? Well, now my new r times 2, that gets squared. And that gets me 2r squared, and that's really 2 squared and r squared, right? 2 times 2 is 4r squared. And so that tells me when I doubled the distance, I put a 4 down here, and if I divide one side by 4, I've got to divide the other side by 4. So when r goes up by 2, if r goes up by 2, then the force actually gets divided by 4. It gets divided by whatever our distance is, changed squared. And so instead of doing this whole big long thing, we can just say, okay, well, we started with one thing, and then we changed the top by this much and the bottom by that much and work it out. So if I had, say, 2 charges, and the force between 2 charges was equal to 12 newtons. And then I took and I triple the distance, double one charge. What's the effect? Well, remember, force is proportional to the charges, Q1, Q2, over r squared. And so what I'm going to do is I'm just going to go ahead and put in the things that I've done. So I'm going to say, okay, instead of Q1, we're going to triple that. So it's 3 times Q1, Q2, over, and instead of r, oh, we doubled the charge, sorry. We're going to put it at 2 there. And we tripled the distance. So instead of r, I have 3r, and so I've got to square that. And so what this ends up with is 2 times Q1, Q2, over 3 squared is 9r squared. So you can see we started with Q1, Q2 over r squared. Now I have 2/9 of that. So I have 2/9 of what I started with, so I have to take 12 times 2 over 9, which is 24 over 9. And you can just leave that as a fraction. If it works out even, go ahead. Or put it in your calculator and get a decimal. It doesn't matter. Just keep track of those changes.